Hello, welcome. This is the English track Houdini talk. We had a wonderful one yesterday in Russian, and so we're going to be following up today to give a slightly different version of it. And like was mentioned, my name is Patrick Kettner. I work at Edge at Microsoft. I'm a member of a number of different spec working groups and as a part of Edge. And I've been doing a number of work inside of our browser in order to investigate and potentially implement parts of Houdini. I do work at Edge, like I said, and it's been really cool being a part of a browser because I've been using the web since it looked like this. This is the this is Mosaic, one of the very first web browsers on the internet. And back when this was what the latest technology was, when Tim Berners-Lee created the web, there wasn't ever it was never intended for web developers to actually be able to control the way that documents looked. When Tim Berners-Lee actually implemented it, he felt that people should, give out information, and the user should be able to control everything: the font size, the colors, the fonts themselves, images, everything. And while that was theoretically, pure in a lot of ways, it rifled a lot of people the wrong way. This is a somewhat famous email sent out by Mark Andreessen in 1994, where he's basically decreeing that it's embarrassing to recommend the web as a platform for people to develop against when they can't even match layouts that you can do in Word or text or any other, really common markup that was used around that time in the educational space. And it's not that surprising that not too many weeks later, he actually announced the Netscape project, Mark and a handful of other people. And one of the very first features that they implemented in this browser was one of the more revolutionary things at the time, the center tag. The center tag was the first time that people could actually control the layout of a page outside of injecting a whole bunch of spacer images or things like that. It was not really possible to control the way a document looked before this. And once we had that, things started to kind of move forward. There was a number of different discussions on how we could actually style documents. There was everything from JSS for JavaScript style sheets to XML styling that was trying to be brought over from some of the other XML-like markups to this, the cascading HTML style sheets proposal by How Come Lee. This was something that eventually became what you and I know as CSS after these two gentlemen. Bert Boss on the right-hand side and How Come Lee on the left-hand side met in Boston in the mid-90s at the world's first web developer conference. About 140 web developers, which was nearly every single one of them in the world. They met together, they started working on what eventually became CSS. And a couple of years after they created CSS, it shipped in IE3. This was about the sum total of what you could do in CSS. You could style text, you could set color. When Chris Wilson, who's now at Google, working at Chrome, was working on IE3 at the time, he decided CSS was the thing that made the most sense. He shipped it, and kind of the rest is history. However, most CSS didn't work. This is the early acid test in that same browser, and it's terrible. It should not look like this, in case you're not clear on what it should look like. It actually looks like this. This is IE5 for Mac, which was the first real browser that had CSS compliance. It's the first browser where you could actually write CSS and it would work the way that it was supposed to work. This was done by Attentek Celik a number of years later. And with the arrival of IE5 for Mac, we had what is now referred to as the layout pipeline, the browser's internal rendering pipeline. The terms will be different between browser to browser, but this general concept of how browsers render pixels, they take your code and put stuff onto the screen, has existed since IE5 for Mac to now in every single browser. It's a number of different steps that happen sequentially. The first of which is the networking step, which should be pretty straightforward. It's what it does on this. It is what it says on the tin. It loads stuff from the network, and then it loads a document. However, one caveat is that even when you're offline, if you're loading from a local file, that still counts as networking. Just getting those text files into the actual browser is what counts. Once we've finished our networking step, the browser can move on to parsing, if it's applicable for any type of text document. Parsing I covered yesterday in my earlier talk, but effectively is just breaking down your files character by character to tokenize it into individual pieces, apply meaning to it. It's to make sure that the browser can understand the text file that you've sent down. Once we have parsing done, we can move over to the DOM step. That's where we will create our object models from both our DOM code, HTML, as well as our CSS, and any other type of tree-like structures that we have to make. Once we have all of our trees created inside of the browser, we can move on to our style steps. Style steps are when we step through the document from the top to the bottom and start going through all of our style sheets on the page. We try to look for the most specific tags that will match and things override. It's just how basic CSS works if you've ever written CSS. This is, internally, effectively, an incredibly simplified version of how it actually is functioning inside the box. Once we have our styling done, we understand what things should look like, where they should be. We need to figure out where they should be. So we do our layout step. Our layout step is similar to our style calculations. We're just going through each individual rule, and we're determining things like placement, box sizing, layout sizing, where it should exist on the page, etc. One caveat that may not be clear is that eventually everything inside of the browser has to render to pixels. There's all kinds of really convenient methods for doing sizing inside of the browser, whether it's EMs, Vmax, VW, VH, percentages. All those things are great to author at, but as far as the actual screen goes, it's more or less useless. So at this point, that's when we determine what exactly is 10 ems or what is 50%. We convert those over to pixels, and then we render them into the actual box model inside of the browser. And so once we have everything converted, we can move on to the next step, the paint step. Now, painting is where we take every single property that has to do with either placement or representation of that image. So stuff like background styles, border styles, layout, location, etc. And then we can rasterize it, send it over to the GPU, and it will convert all of those vector-like elements over to an actual rasterized image. So even your vector stuff, things that don't actually have pixels as you would normally think about them, have to be converted to pixels eventually to be put on the screen. The paint step is where that happens. Now that we have things painted on the GPU, we can compose them or composite them into an individual piece. Now, I was a little bit hand-wavy before. There was one piece that I was not entirely clear about, and that's because the layout didn't actually look like what I just showed you. It looks more like this. When we're laying out each individual element, we're laying them out kind of as separate, unique pieces. The compose step is where we end up stacking all of those pieces one by one. That way we can make sure that we can draw the fewest number of pixels possible. Normally, with something as simple as this, a layout as simple as this, it'll end up being composited down to one individual layer. A method that became really common a number of years ago, though, was adding something like this, a Translate 3D hack. What that was doing was effectively elevating that thing to another layer. Browsers try to optimize things to make it as simple as possible to paint. So if you ever see this kind of a piece of code being used inside of your code base, or you see stuff like will change, all that it's effectively doing is elevating that one element to its own layer, so that it doesn't have to so the browser doesn't have to composite the whole thing all at once. It just composites that one little piece. It can move it. And this is why it's a lot more efficient to do stuff like translate or change opacity than it is to change top or left or position absolute. When you do top left, you have to recomposite the entire image, whereas if it's translated, it can be a separate element on top of the GPU. Meaning it's fewer pixels to draw and much more efficient. So now that we have everything composited and we understand the pipeline of the browser, the one thing that I didn't explain, though, is that every single time that you touch this pipeline, it has to go from the left to the right. So if you end up touching the parsing stack or the DOM stack, you have to go through styling, layout, paint, composition, etc. That's one of the problems that Houdini was introduced to try and solve. See, the only API point that we actually have the ability to interact with up until now is through the DOM APIs. If we wanted to add a class to an element, it has to go through the DOM API for adding a class, then we have to recalculate style, layout, etc. If we want to find out what a padding value is, we have to go through the DOM API. It has to query the styles, the layout, etc., 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 and it can be really, really slow. And that sucks. To make anything performant on the web, it's really, really difficult. It's an uphill battle. And this is something that the web has kind of been suffering with for quite some time. Take, for example, CSS Grid. This is something that was introduced recently to the web, and it's been it has really wide support now in browsers. Pretty much all major browsers support it, and that happened really within about 8 months of each other. But CSS Grid wasn't a new idea. This is something that actually came from Windows 10. It was introduced in Windows 8, and it was introduced in IE 10. It had a really early version of CSS Grid because most of the operating system was based on grid-like layouts, and internally, Microsoft wanted to use CSS to lay out a number of their own native apps. We created a new spec at Microsoft, and it became what is now CSS Grid. However, it took 5 years for that spec to actually reach other browsers for a whole bunch of different reasons. During that time, there were polyfills that were created, like the CSS Grid polyfill, but it was slow, it was gross, and it's not really a way that you can polyfill something in CSS efficiently. Because of problems like this, we wanted to do something where we could actually polyfill those individual steps of the rendering pipeline with JavaScript. So that you can polyfill these types of CSS features much more easily. So, like I said, previously we've only had that DOM interaction point. What Houdini is exposing a whole bunch of new APIs so that we can interact with a whole bunch of different points inside of that layout pipeline so that we can trigger the smallest number of pipeline flush as possible. So this is what Houdini ends up being. It's a collection of APIs that gives us a whole bunch of new access points in order to make the most efficient code possible when either interacting with layout on the web or implementing CSS polyfills or really just doing anything that has to do with styling on the internet today. Some of these APIs are the CSS Properties and Values API, the CSS Object Model, a collection of things called the Worklets that we'll jump into in a little bit. And there's also stuff like the CSS Parser and Font Metrics API. So diving straight in, the very first thing to talk about is the Properties and Values API. This is also known as custom properties, but most people call it CSS variables. Most browser engineers hate that term. Custom properties is technically about as risque as they get with how it's going. And this is something that's supported really, really widely. I use it all the time in my production sites. I hope you guys are as well. And if you aren't familiar, which I think most people are, this is what that code ends up looking like. You set this new type of custom property. It's a dash dash, then a string, in this case, dash dash distance, and you set it to any CSS value that you want, any type of value that you want, really. And then you can reuse it later on in your code like this. So in this case, we are setting a distance of 400 pixels and then setting the width and the height to that same value. And then we want to do something like this, where we animate on hover, so that if your mouse moves over that element, then it goes down to 150 pixels. Which theoretically should be fine, but in practice, when we end up doing it, we just get this weird snappy element. The reason why that is happening is because of our CSS variables. And that arrow is broken. That's actually supposed to be pointing over on that distance level. And the problem is that the CSS value that we're setting up here, that 400 pixels, isn't actually the CSS value of 400 pixels that you would think about. It's really just a string as far as the browser is concerned. It's just 400px. There has no intrinsic value to that. It has no way to know for a fact that you're talking about the actual pixel value and trying to animate between them. And as a result, since it's just a string, you can't animate strings. How do you animate from one string to another? You don't. You have to give it semantic meaning. And so that's where Property and Values API comes in. Property and Values API ends up looking like this. It's the css.register property. And you pass it in an object with just a couple of properties. The only one that's technically required is the name, and that just is a reference to your custom property that you're referring to. And then you have a syntax. Syntax is any one of these types of properties here, and it's just a way to declare that this is a color type, this is a length type, this is a X type. Every single type that exists inside of CSS has a syntax type that it maps to. And so in this case, we have our 400 pixels going to 150 pixels, and those are both lengths, and so we set our syntax to the length type. If you wanted to animate from a color, like say from red to blue, you set your syntax to color, and the browser just treats it as though it is a custom color, etc. Ultimately, you can also set an initial value as well, so that if you remove that property and you want to animate between a non-existent version of that property and the existent version, you can animate from what that initial value is. In this case, we're setting the initial value to 0. And now, when we mouse over that element, it animates smoothly, which is great. Everything works. And hooray. Now, one thing that's not entirely clear, though, and can be confusing, is that syntax. This might look like it's kind of pseudo-syntax or not real code, but that actually is what you're supposed to write, that angle bracket, length, angle bracket. And what that represents is a kind of new API called the CSS OM, or the CSS Object Model. Now, technically, just like we have a document object model, we've always had a CSS object model inside of the browser. It's just we've never really exposed it in a way that developers can really use. In this case, what we're talking about isn't really just the CSS object model, but the typed object model. What that is it gives a whole bunch of new APIs that exist on top of a lot of standard CSS interaction points that allow you to get stuff like your values, your units, and all kinds of other pieces that I'm going to dive into in a second to allow you to have much more efficient access to the rendering pipeline without having to parse a bunch of strings. So let's take, for example, this box. We have some text inside of it, and let's say we wanted to get the width of that element, right? So we can do get computed style of the element and call width, and it'll be equal to about 200 pixels, which is fine. However, when we go ahead and add a bunch of text to this to where the scroll bar gets introduced, we end up having a problem. The width is no longer 200 pixels. It's actually 187 pixels because that scroll bar is 13 pixels. As a result, in order to know what the width of that thing is, we actually need to have this kind of gross code where we call get computed style, and then we end up having to parse a whole bunch of floats because it returns 0 or 0px or 100px or all these different things for padding or border, a whole bunch of different things in order to actually know what the concise value will be. We have to do that string manipulation and then return that entire value. Now, with the properties and with the typed object model, what we're able to do is variate that slightly so that rather than calling get computed style, we have this new API called get computed style map. Pretty much all of the CSS typed OM interfaces are the exact same APIs that you've traditionally been using, just with the word map added to it. So get computed style map, element.style map, etc. So in this case, what the difference ends up being is that rather than returning a string representation of your value, you actually get an object representation of your value. So rather than 200px, we have a style.paddingright.value. And that value will be 200, the integer. So you have direct access without having to do string manipulation. While that might sound like a not that convenient of a thing, keep in mind what's happening underneath the hood. Previously, we had to do the DOM API to the string, take that string, parse it, and then do all of our calculations against that parsed number. Now we're just going from the DOM API directly to our calculations. While that might not sound like that big of a deal, under the hood to the browser, that's a really big deal. Every single millisecond you're able to shave off of your tight loops for polyfilling, CSS features, layout features, can add up really, really quickly. Keep in mind for 60 frame per second interactions, you only have 16 milliseconds to do all these sorts of things. If you're trying to lay out something that's hundreds of thousands of pixels wide, every single thing adds up. Like I said, a lot of these interactions on the CSS typed object model are just adding the word map to things. So get computed style map for an element, and you will use that to query any computed value. So anything that could be inherited from its parents. There's also element.style map for styles that have been set explicitly. So just like if you would normally call element.style to get its inline CSS values. And then, so the examples that I gave before were pretty silly. There's not a lot of value on things like this where you're able to just check 200 pixels. You could pretty trivially figure that out without this. Where you can, one thing that is convenient though is you have the ability to get unit values, so you can check things to see whether or not they were set in pixels, ems, vmax, etc. Where this API, jumped ahead of myself. You can also set these values with using things like a CSS unit value. So in this case, we're setting it to 50 EMs. This is nearly equivalent to just setting, element.style .width equals 50 EM as a string. However, it's just going to be a lot more efficient underneath the hood. It skips a whole bunch of parsing code that the engine normally has to do. Now, where the previous examples have been pretty silly, where the typed OM starts to really shine is when you get into more complex CSS interactions. So take, for example, background position. If I were to ask you, how do you describe what is that actual background position in a way where you have to parse the CSS to explain it, it gets complex quickly. However, with the typed OM, you can do stuff a lot more understandably. We can do document.querySelector, grab that style map, and then we can just grab the X and Y interaction, the X and Y values off of that element. So since it is the center, its X value will be 50 with a unit of percent, since it's exactly centered, and its Y value will actually be 100% minus 10 pixels, because it's bottom 10 pixels. So it's all the way to the bottom and then up 10 pixels. This is something that can be really, really complex to actually parse out and understand yourself, but it's something that can be really useful when you're writing these types of polyfills that Houdini was made to do. None of this is very simple or easy to use or anything like that, and that's because Houdini isn't really about ease of use. It's about efficiency. It's about making the browser work as fast as possible and empowering web developers to be as useful and as to make their code just absolutely scream on top, inside of the browser engine. Now, there's a whole bunch of different values that you can set inside. Basically, every single type that actually exists inside of CSS, you can explicitly set using the CSS type.om. Excuse me. And one of the things that I really like about the type.om spec is actually it's really, really straightforward. This is the W3C specification, and while it might seem a little bit overwhelming if you're not familiar with specifications, this is one of the more straightforward ones once you're able to understand the beginnings of it. If anybody here is interested in working with specs or contributing to browsers, I really recommend you take a peek at this specification. It's pretty straightforward to get involved with, and I'd be happy to help anybody here. Now we can talk about the little bit more interesting stuff, worklets. So worklets are something that have a bunch of worklets are one of the newer, more exciting concepts that are coming to browsers as a result of Houdini. And before we dump into the individual ones, I just want to give a high-level concept of what they are. Worklets are kind of based on web workers. You can think of them as really lightweight versions of them. Web workers have been around for a really long time, nearly 10 years actually, in just a few weeks. They were added to Safari. And the idea behind a web worker was that you have an element, you have a page, you call a URL as a string, and it basically loads up another thread in the browser. From that thread in the browser, you're able to post message, whether it's through text or an object, have it do something, interact with it in a JavaScript environment that doesn't have access to the DOM, and that way it doesn't block any of your UI rendering. It's able to do stuff, calculate, run functions over your stuff that you send to it, and then it's able to send back a result. Once it does something, once you have that result, you're able to effectively, the purpose is effectively to offload a whole bunch of heavyweight calculations and functionality to other threads. So web workers are really, really basically the idea of threads in the browser. You can have more or less one web worker for every core of your computer and have it run without a problem. Not only that, web workers are heavily event-based. So they only do something when you request it to do something. You post a message, it calculates something, it sends something back, and you react to that event. Worklets, on the other hand, are much more lightweight, theoretically, and they're also, while they are a separate JavaScript environment, they are actually API-based. The idea behind a worklet is effectively a function that you're providing to the browser to do a thing when it needs to. Those things could be paint a pixel on the screen, calculate layout of the document, it could be calculate an animation, all kinds of different things. This might be happening thousands of times per second. So your worklets need to be really, really lightweight, and they need to be as fast and efficient as possible. Not only that, they are thread agnostic. It has nothing to do with threads. A browser might literally spin up thousands of these things simultaneously in order to run all the calculations on the page. Workers, on the other hand, are way too heavy inside of the browser in order to actually make that useful. And that's why this new concept of worklets was created. One key thing to keep in mind, actually, is that there will always be a minimum of 2 worklets whenever you're using one. That's in order to prevent people from relying on state inside of worklets. Browsers spin up at least 2 of layout, animation, compositor worklets in order to make sure that you're not storing variables and then referencing them later. They'll just swap between a minimum of 2 constantly in order to get it to work. So the very first one that I'm going to touch on is the layout worker. Layout worker, which is also known as the CSS Layout API, ends up looking a bit like this. So we have an element with HTML, and we have our CSS that we declare some normal CSS stuff. The only thing that you might notice is different is this display layout property. Inside of it, we are passing a string called masonry. That layout as a function inside of display is a pattern that's really common within our worklets, and it is effectively just calling one of the idea of layout as a function or paint as a function. It just is calling calling a registered worklet that we are going to be setting up in just a moment. So from there, we have window.layoutWorklet.addModule. That pattern is going to be the same across all of our worklets that we'll be talking about. We have the ability to add a module that's an external file. In this case, masonry.js. Unfortunately, I get frustrated at this point because I only have about 5 minutes to talk about the rest of it, and there's really, really complex concepts inside of layout worklets. I could go on for 5 minutes, or 5 hours, not 5 minutes, talking about this, because we have stuff like resolving inline style, borders and padding, variant space, block sizing. It's gross. There's a lot of stuff inside of the browser that's really, really complex, that's really, really difficult to express in such a short amount of time. And not only that, it's really complex for browsers. Chrome actually just spent the last 3 years re-implementing their entire layout engine in order to make Houdini work. That's because they're based on WebKit, which is based on KHTML, which is based on code even older than that. And back when that project and the layout engine that they were using was created, all of these terms hadn't even been created yet. All the things that we're talking about inside of these specifications that Houdini is supposed to map to didn't exist. And so they had to completely redo this. It's very, very complex, and unfortunately I can't really dive into it that much. But again, it's not about efficiency. It's about it is about efficiency, not ease of use. There's a whole bunch more information at this API, at this URL, if you want to learn more about the layout API, or I'd be happy to talk to anybody here afterwards. One thing that I wanted to point out, this is one of the official Masonry demos that has been given out by the Chrome team. This is a really, really fast evolving specification. In fact, here we're looking at using generator functions. It's a special type of function that does things. But this has actually been removed from the specification as of like 3 days ago. It's completely changing, which means that every single demo, every single example, pretty much every talk that goes over this is already out of date, even though they just changed this days ago, which is a good thing. Generator functions are really gross to use in this context, and I'm really glad that they made this change. But layout functionality, especially inside of the browser, is complex and fast evolving, so sorry. One thing that I can cover in a lot more quick amount of time is the paint worklet, which is also known as the CSS Paint API. The setup for this is really, really similar to what we just did for the layout worklet. We have an element, we have some CSS with some normal background color, height stuff we would normally set anywhere. Then we also have our background image, which is the paint as a function, just like we had layout as a function to call in Masonry. We're calling paint to call QR. And then we're setting a custom property here of a QR URL, which is just my personal website. And then inside of our script, we're calling paintWorklet.addModule and an external script. Now, that external script here, we can go ahead and import, just like we would any ES6 code, an existing QR code library, and from there we can call register paint. Inside of all of our worklets, we have this concept of registering foo, so register layout, register paint, register animation. And that's where we pass that string that represents the thing that we're calling when we, inside of our CSS, when we call in paint QR, it's referencing this string QR that we're referencing there. Have an ES6 class, and then we end up calling static get input properties. This is something that exists in all of our worklets, and the idea of getting input properties is to let the browser engine know what properties you actually care about, so that it doesn't necessarily have to calculate every single CSS property simultaneously. It can render these things as efficiently as possible. Since I only care about our QR URL, that means the browser doesn't have to calculate box sizing, placement, layout, opacity, any other value. It can just return that string and therefore skip a whole bunch of calculations. From within that, I call paint. And that paint API is a part of the paint worklet. And we're given 3 arguments inside of our paint worklet. We have our context, CTX, our geometry, and our properties. Our properties are the things that we just declared, get input properties. In this case, we're only getting the 1 since we only care about the QR URL value. And then we're going to calculate a minimum size. This is just something I needed to do for my QR code to make sure that it was square. And we can call geometry.width and height. Geometry is the known width and height of the element. And then from there, we're able to, if that URL exists, we're just going to call qr.draw, which is just importing that QR code version. So as a result, you can get this QR code that's painted as a browser as fast as possible whenever the browser needs it to. With just a little bit of script, you can add stuff in order to make it dynamic. So in this case, we have it so that whenever the Since it's a text element on input, we're just going to set the property. So we're setting the CSS property of QR URL to whatever that text value ends up being. And so we can type in, and it changes stuff. I have less than 10 seconds, so unfortunately I can't go over the animation stuff, but just the takeaway message of this should be that it's about efficiency, not ease of use. Please start playing with Nightly, start playing with Chrome. As a browser, I can tell you that in order to really understand what developers want to have on the web, we look to you to see what you're actually using. Start shipping this stuff in your actual sites in order to tell browsers like Edge, Firefox, Safari that you want it, and we'll implement it. Most of all, give feedback. You can go to this URL in order to let us know that you're interested in Houdini, to vote it up, to say that you would use it if it existed. And then ultimately, thanks. You can find me here on the internet, and feel free to find me later. Cheers.
Thanks, Patrick.